So what is it that I've done? I've collected all the terms in three terms that I'm multiplying. And so, for instance, if we're looking for the term here, where is that? Well, I get that from taking this term and this term and that term, because the I plus t squared inverse cancels out with the I plus t squared. All right, and of course, this term here, where is that? Well, I get this by this term and that term and this term for the same reason as before. So that's just a way of rewriting things. So I will say this is the identity plus t alpha squared. What happens inside the parentheses? Well, the big parenthesis in the middle, I can just write it out. I get t alpha plus t alpha t squared minus t alpha square t, and then I have 1 plus t squared inverse as before. And now I will collect some of the terms. So I take I plus t alpha square, and I take t alpha minus t. So I take these terms here and I put them here, and then I take the remainder. Then of course I need the left hand side, and now I take the other terms. So I get I plus t alpha square, and then I have this time t alpha t square minus t alpha square t, and I plus t square. And I think I've forgotten some inverses all the way back here. And there. Okay, so now what can I say about this? Well, if we're remembering the way we defined h, then the first term is h of t alpha, and then I have t alpha minus t, and then I have h of t. Right? But I can also take, so that's just the first term, but I can also take and rewrite this middle term here. So I need a new color, let's make it red. So this middle term here, I can rewrite that as t alpha, and then I have t minus t alpha, and then t. Right? So that collects all the terms. So if I take the t alpha and I put it in to the left term, and I take the t and I put it in the right term, then what I have here is g of t alpha, and then again t minus t alpha, and then g of t. Okay, so that was a long rewriting, so I'll just rewrite it. So in conclusion, so what I got from this long computation is that g of t alpha minus g of t I could rewrite as h of t alpha minus t, h of t, write it like this, plus g of t alpha t minus t alpha g of t. Right, and of course I want to convince you that g of t alpha converges to g of t in the strong operator norm, so let's apply it to some vector x in the Hilbert space. So that's the same as applying this one to x and applying this one to x. And I'm claiming that this will go to 0. Right? So why is it that this goes to 0? Well, h of t applied to x is just some vector, right? So t alpha minus t applied to that vector will go to 0, because I know that t alpha goes to t in the strong operator topology. And the same is true down here. This will, maybe put it like this. This is a fixed vector, so this will also go to 0. But we have, in front of this, we have h of t alpha and g of t alpha that is a little bit hard for us to control. Right? So I don't really know what happens on h of t alpha and g of t alpha, but I do know that the norm of h of t alpha is less than or equal to 1. And I know that the norm of g of t alpha is less than or equal to 1. And how do I know this? That's simply because the functions h and g are made in such a way that they never attain values that are bigger than 1. Right? So in my drawing, it looks like the function moves on the other side of 1, but that's just because I drew it wrong. Right? So clearly this function is 1 at, the green function is 1 at 1. Right? So I've simply arranged it so that these operators to the left of my computations are bounded in norm. So whatever they do on a sequence of vectors that go to 0, that will still go to 0. Right? So I can conclude that it goes to 0, and that's precisely what I was after. So my next claim, number 2, is that suppose I have some arbitrary functions, call them f1 and f2. They come from S, and suppose that f1 is bounded. Then I claim that f1, f2 is also in S. So this is almost straightforward. So I'm applying the function f1, f2 to t alpha, and I compare that to f1, f2 applied to t, assuming that t alpha goes strongly to t. Just like before, it's in B of H, SA. Right, so let's write out what this means. So this is just f1 of t alpha, f2 of t alpha minus f1 of t, f2 of t, and then I will add and subtract something to give me something I can work with. So I'll just remove f1 t alpha, f2 t, and add it again. f1 t alpha, f2 t minus f1 t, f2 t. Right, and we're trying to work out what happens when we have convergence in the strong operated topology. So apply this to some x. So we apply this to some x, we apply this to some x, and we apply this to some x. And now we can rewrite this as f1 t alpha, f2 t alpha minus f2 t applied to x, plus f1 t alpha minus f1 t applied to f2 t of x. Right, so, and I guess we're putting norms on things here. Using the triangle inequality, I'm going to have to move this like this, and that is then the same as this, but now I know that f1 is bounded, so if I do like this, I can make this smaller than some constant, namely the uniform norm of f1, and now I have f2 t alpha minus f2 of t applied to x plus f1 t alpha minus f1 of t applied to f2 of t x. Right, so I mean, I don't know if this long computation helps, but the point is of course that I know that f2 is in S, so I know that when t alpha goes to t, f2 of t alpha goes to f of t, f2 of t on any vector. So that explains why this term that I made in red goes to 0. And of course you might be worried about what happens with the f1 of t alpha, but just like before, this is something that goes in front and is bounded in norm, so it cannot change the fact that the limit is 0. And here I have the same situation. I know that f1 is in S, so f1 of t alpha goes to f1 of t applied to any vector. So vector in question here is not x, but f2 of x, f2 of t of x, but that goes to 0 as well. So the whole thing goes to 0. So, oops. Now we can conclude that, in fact, also the function that we called h lies in S, because if we perhaps write it out this way, so h of t is 1 over 1 plus t squared, so we note g of t is t over 1 plus t squared. So if we write it out this way, we say 1 over 1 plus t squared plus t squared over 1 plus t squared. This, of course, is 1, but maybe write it like this. And then if we go through what we know, we've seen that this is in S, we've seen that this is in S. But by the previous claim, also we've seen that this is in S, and we've seen that when we multiply two functions, knowing that one of them is bounded and both of them are in S, then the product is in S. So this is also in S, right? And of course, S is closed under, it's a subspace, so it's closed under subtraction and addition, multiplication by constants. So that means that this, which is my h, is also in S. So claim number 4, if I have an f that lies in S, so does the complex conjugate of f. This is really a more fundamental observation. The map t goes to t star is strongly continuous on the set of normal operators. So we've seen that it is not strongly continuous in general, and it's fairly easy to see. Suppose we have t alpha converging to t strongly, and then we look at the difference between t alpha star and t star applied to some vector. So we think of this as an inner product with a total of 4 terms. So if we collect these 4 terms, they will look like, maybe I'll put them here. They will look like t alpha star x, t alpha star x with a plus, t alpha star x, t star x with a minus, t star x, t alpha star x with a minus, and then tx, sorry, the stars with a plus, right? But the point is that we have assumed that t alpha is, both t alpha and t are normal. So this means that if I move this on the other side with a star, right, this will give me T alpha star x x. But now, since I've assumed that my elements are normal, I can commute these two elements across each other, so that gives me T alpha star T alpha xx, and now I can write this as T alpha x by just moving this one back to x, right? So using the normality, I can rewrite these terms as T alpha x's square, and I have tx's square, and then I'll move the terms. Of course, the two remaining terms that I have with a minus on, I cannot just commute T alpha and T, because I'm not assuming they commute, I only assume that they're normal. So that will give me x comma T alpha T star x, and then x comma T alpha T, sorry, that's what I already had. It must be T alpha star x. Right, but then let's see what happens when we let alpha go to infinity. So when we let alpha go to infinity, T alpha x goes to tx, so that just gives me tx square. Tx square, I have this twice, and then I have x comma, and then what happens? Well, when T alpha goes to infinity, T alpha T star x will go to T star x, and when T alpha goes to infinity, T alpha star goes to, hang on, of course I did this wrong, right? I mean, it's not nice to have it situated here. I would rather have it here, right? So, okay, let me, sorry. This is not a good way of writing it, so I'll rewrite it like this. So it will be minus T alpha T star x x. Now when this converges, this goes to minus T star x x, right? So I have placed the terms in the wrong place. But then we see that these four terms are all the same. They are the length of the vector c x squared, so it all goes to 0. Right. So this computation tells me that taking stars is a strongly continuous operation if we restrict ourselves to the normal operators. And then it's clear that when, so what we're trying to prove is that when T alpha goes to T strongly, we know that f of T alpha goes to f of T strongly by assumption, right? But f of T alpha and f of T are normal. Why are they normal? Well, they came out of the functional calculus applied to some normal elements, actually self-adjoint elements, right? So I know that they're normal. So when I'm looking at f bar T alpha, which is just f of T alpha star, this converges strongly to f of T, which is star, which is f bar of T. So that takes care of my claim number 4. And now I'm beginning to be ready to close this off. So the fifth claim is that we set S naught to be S intersected with C naught of R. So what I mean by C naught of R is functions that are continuous and vanish at infinity. And then we claim that in fact S0 is everything in this case. And we will do this using Stone-Weierstrass. So Stone-Weierstrass, in the case where we have functions vanishing at infinity, looks like this. So if, let's say, A inside C0 of R is a subalgebra which is closed under complex conjugation, and separates points in the sense that whenever I have x and y in R that are different, there is an f in A such that f of x is not f in y, and separate all points from 0 in the sense that whenever I have an x in y, also an x in R, there is an f in A such that f of x is not 0, then A is dense in C0 of R. Right, so what I'm trying to do here is to state a version of the Stone-Weierstrass theorem that works in our setting, where of course the space that I'm working on, the reals, is not compact, right? So you prove this version of the Stone-Weierstrass theorem by passing to the one-point compactification of the reals, right? So instead of working with the reals, you sort of compactify it into a circle where you have an extra point infinity, right? And what happens then is that all the functions that lived on R and used to vanish at vanish at infinity, they now become functions that are 0 at infinity. Right, so this means that the functions that I'm looking at, they are generic functions, except they're all 0 at this added point that I got when I one point compactified. And then the assumptions that I have here is that this means that the points are separated, the old points in R, x and y, are separated by f, and this condition here is that we're also separating points from the infinity point, right? Because all the functions that I'm looking at, all the functions in A in particular, are 0 at infinity, so I need to separate that as well. And that's the concept, that's the point of the second assumption that I'm putting on A. Okay, so this is really the way Stone-Weierstrass looks, and in a sense, I'm kicking myself a little bit because last year when I gave this lecture, I was telling myself you should really do it over the reals. So when we proved the Stone-Weierstrass theorem, you may remember we did most of the work in the reals, and then we sort of passed to a complex version. And in fact, since at the end of the day, I want to know that functions that look like this are continuous in the strong topology. In particular, these are real functions. I could do everything real in a real setting, and then I wouldn't have to deal with proving that essentially my claim number 4. So that you could sort of wait. There's a little bit of waste of time in the context here, but I don't have the energy to go back, to be honest, and do a brand new pencast of the first part of the Kaplansky theorem. So let's do it this way. It's not wrong. It's just slightly inefficient. Okay, so why am I doing this? Of course, I want to use the Stone-Weierstrass theorem, and I want you to note that S naught is separating in the sense that I explained before. And why is it separating? Well, that's because we have put two functions. One looks like this, and the other one, actually, let me go back and use the right colors. So one is orange and green. Okay, so so the one function that we've proved was in S, and it's clearly vanishing at infinity, is the one that we called H, looks like this. And then the other one we proved was in H, looks like that, right? So that's the one we called G. And you can see, except that I drew this all wrong. We do it. So something like this. This is G. I'm still doing it wrong. Okay. So it seems to be impossible for me to draw this right without drawing a y-axis. So I'll put that in. And then it goes like that. Okay, so that's G. Right, and we can see that we can use H to separate all points from 0, because H is a function which is never 0, even though it vanishes at infinity. And we can also use it to separate all points from each other, except if we have x and minus x. They, of course, go to the same thing under H, because H is an even function. But then we can just use G to separate those 2 points, because G is an odd function. So that's how we can see that S0 is separating. And it's also is a subalgebra, because we've seen that when we multiply 2 functions in S, knowing that one of them is bounded, in this case both of them will be bounded, then the product is in there. And closed under conjugation. And so that means that S naught by the Stone-Weierstrass theorem is dense. So in fact we can do better. S naught is closed. This is more or less trivial. I'll just say by an epsilon over 3 argument, because if I have a function which is close to a function in S naught, then you just sort of pull the elements apart in an epsilon over 3 argument, and you can see that S naught, that function also lies in S naught. So S naught is everything. And now finally we're ready for the last part of the proof, and that says that now if maybe I'll write it like this. So if I take S and intersect it with the continuous and bounded functions on R, I get all the continuous and bounded functions on R, which is what I wanted to prove. So for this, I will fix some function f that lies in CP. And now I note, for something that we've already done, is that if we take the function h and add to that t times the function g, we get the identity. Right? So this we've already seen. So what happens now if we look at f of t times h of t plus f of t times g of t? This, of course, is f of t, right? And my aim is to prove that f of t lies in S. And what I know about f is that it's a bounded function, right? So what can I do at this point? Well, I know that h of t lies in S naught, right? So that is a function that vanishes at infinity, and hence it lies in S naught by claim number 5. So it's a bounded function, and I'm multiplying onto that. So it's a bounded function that goes to 0, right? So it lies in S naught. But I can do better than that, right? Because this actually also lies in S naught. Because h is a function that vanishes at infinity, and I'm multiplying on it my f, which is bounded, right? So it vanishes at infinity, and hence it lies in S naught. So I want to do something similar in this term here, right? But I need to be really careful because it is not true that that this product lies in S naught. Right? So I have to be really careful. I'll write it as S as t times f of t times g of t. Right? So g of t is in S naught. And then so is f of t times g of t. Right? So this is now a function that vanishes at infinity. It's continuous, hence it lies in S naught. And I do know that t, of course, t is not in S naught. It doesn't vanish at infinity, but at least it's in S. And then I've proved that the product of two things that lie in S also lies in S, provided I know one of them is bounded, and of course this one is bounded. So this lies in S. Right? So f of t cannot lie in S naught because I haven't assumed that it vanishes at infinity, but that's okay. I now know that it's in S because it's a sum of something from S naught and something from S, and hence it is a function that gives me strong continuity as I need in the proof of the Kaplansky theorem.